All right. So where do we leave off last class? We were talking about simple linear regression, mainly focusing on interpretations. But remember what we were doing was we were trying to predict different y values given different values for x, or understand this relationship that existed between x and y, whatever these two variables are. So we ran this regression, minimizing the sum of the squared errors that allowed us to come up with some sample coefficient estimates for the intercept and the slope. So we only had one sample, but we want to think about what if I were able to sample it 1,000 times? Well, if we go back and remember what we were doing with sample means, we said, let's say I had a population data set and I sampled from it 1,000 times and I saved those 1,000 different sample means. If we then plotted those, we saw that they were normally distributed and they were going to be centered around whatever that true mean of that y variable was. Okay. We also said that the variance of our sample means here was going to be whatever the original variance or sample variance we calculated from our data set was over our sample size. We usually were using that standard deviation. So how do I go from a variance to a standard deviation? Simply taking that square root, right? We then said, okay, any sample mean value that I see, if I have some assumed true value for what that population mean is, I could turn that into a test statistic by taking this sample statistic that I found, the sample mean, subtracting the assumed true value of the population statistic, or the population mean in this case, and then dividing by the standard deviation of my statistic here, which was a sample mean. So we would plug in here that square root of our sample variance over our sample size. Okay. So this was kind of what we did before. Let's now think about if I were to take 1,000 different samples and run this simple linear regression, estimate what that slope and intercept coefficient are. Now I'm going to write this out for the slope coefficient. The same thing would be true for the intercept, and I'll kind of show you this in Stata here in a second. But if I'm looking at the estimates for this slope coefficient, they will be centered around whatever that true coefficient would be if I had the population data. Not only that, right? We also have, and here I'm going to write it not technically correct for right now, but just for the sake of starting out, we also kind of have a standard deviation for that sample coefficient. Now, we'll end up calling this our standard error. So what this ends up being is, excuse me, excuse me, is if we were to take the square root, right, of the sum of our predicted errors over n minus 2, and then divide that, divide that by the square root of our SST. Remember, we were writing this slightly differently, I think, last class, thinking about the R square, but this was the total sum of squares, right? So this was the total sum of the squares that existed in that X variable, or the total amount of variation that existed in that X variable. So we're not going to actually calculate this by hand, but what you can think of this as the standard deviation of our sample coefficient. It's very similar to that standard deviation of our sample mean. It's just a little bit more complicated to calculate. Now, Stata is going to do all this work behind the scenes for us, right? It's going to calculate the errors for each observations, divide, add them up, divide by n minus 2, determine the total sum of squares is that X variable. So we don't have to do any of this work. But what we can start to think about is, okay, I only have one sample. So whatever sample coefficient I come up with from my one sample, how could I turn that into a test statistic? We can start to do hypothesis testing or build confidence intervals. Well, I've got my sample statistic. It's no longer a sample mean. It's a sample or coefficient estimate. I'm going to subtract. Well, here, it's going to be the assumed true value of our test statistic. Okay. So this gets a little bit weird kind of notationally. Generally, instead of writing this, we would usually use beta 0, but the problem is beta 0 already represents our intercept. So instead of beta, we'll just write this as gamma, right? So this is going to be like our assumed true value of that coefficient. And then divide by, well, it would be this whole thing, but instead of writing this all in every single time, just like we did before, it's the standard deviation of my statistic that I'm now looking at. Now we'll end up calling this our standard error, and usually I'll abbreviate this with just S period and then our epsilon, so our standard error. So if we're thinking about a more simplistic version where I'm not kind of building it and trying to kind of compare to things that we've already done, it's going to look something like this, where we will, in this class, always assume that the relationship that exists between any x and y variable, we're always going to start out assuming that there is no relationship. So if they assume that there is no relationship, this assumed true value of the slope coefficient would be 0, right? We're essentially assuming that if we were to look at that scatter plot, do we have a line of best fit that's horizontal? If we find any evidence that there's any slope to our line of best fit, can we reject that assumed true value of 0? Well, once I have my test statistic, I can do things like say, oh, well, we know that with large enough sample sizes, we know that we should be using that student t-distribution, but we can use our standard normal values to approximate. So when we think about critical values, right, every test that we do in hypothesis testing for this class is going to be, we start out assuming that this true slope coefficient, right, is equal to 0. Right? So we always have a two-tailed test. So we're always going to have a pair of critical values, and those critical values will be what gives us a total of alpha in our tails. So usually we would write kind of, well, it's what value would give me alpha over 2 in each tail. Right? So once we come up with these values, this kind of values we would see from our standard normal to kind of approximate for an alpha of 0.1, 0.05, 0.01. These are our benchmark values. These always end up being critical values of about 1.65, 1.96, 2.58. Now, we have a two-tailed test when we're doing hypothesis testing for these coefficients because we always assume that it's just equal to 0 specific value. So we're always going to have a pair of critical values. Now, from here, once I have my critical values, it's just, okay, is my test statistic in that rejection region? If it is, I can reject my assumption. So if we find a test statistic that's in this rejection region, what we're saying is we found strong evidence there is a relationship, and we're rejecting that there's no relationship. So we have to find strong enough evidence to be able to reject that there's no relationship, or say that we found strong evidence there is a relationship. Now we can also use the p-value approach. Remember, how would I find my p-value here? Well, it would be the area to the right or more extreme than my test statistic. However, for a two-tailed test, seeing something this many standard deviations above that assumed true value, it would have been equally as likely I saw something that many standard deviations below. So we can kind of find this area to the right and then multiply it by 2 to get our p-value. Now, one nice thing in Stata, we're not going to do this by hand every single time. Stata, instead of using a standard normal to approximate, it will actually correctly identify which student t-distribution we should be using based off of our sample size. Excuse me. And then already multiplying by 2, and it just spits out at us the p-value. So we'll kind of take a look at what this looks like in Stata. But it's the same setup as what we were doing when we had sample means. Also, just jumping the gun a little bit here, but since we're already, I don't know, it kind of makes sense to write it all here. So just like when I was building a confidence interval, for my sample mean, I took a number of standard deviations away I needed to go to get alpha over 2 on each side, multiply it by the standard deviation of the statistic I'm looking at. We can build confidence intervals for our slope coefficient going a certain number of standard deviations to the left and the right. Now, once again, we could use the standard normal values to approximate here. Stata is actually going to use the specific student t-distribution values we should be using based off the sample size. Now, our standard deviation of our sample statistic, we said we were going to start calling that with linear our standard error associated with that. Once again, you can think of it as like the standard deviation in those slope coefficient estimates. Okay. So that's kind of everything, relating it to what we've done before. That's kind of where we're going. So here we are, let me make sure. Okay. Yeah. So we left off doing some interpretation. Let's see. Hopefully this is recording okay. I think it is. So my things are a little bit off, but here, when I say that expected value, this was the idea that if we were, instead of take one sample, if we could take 1,000 samples, those 1,000 different estimates we have for that slope coefficient should be centered around whatever that true estimate would be from population data. So we would say this means that our estimate is unbiased, that on average, if we were to take enough samples, the slope coefficient estimate we have is going to be equal to the true population coefficient, or this true population slope. As we get larger and larger sample sizes, we're saying that kind of this slope coefficient estimate is going to be also consistent, right? Or that as we have a larger and larger sample size here, if n is going up, what's happening to this fraction? It's getting smaller. This is getting smaller. What's happening to our standard error? It's going down. So when we're thinking about our test statistic that we had before, that was in our standard error was in our denominator. So if our standard error is getting closer and closer to zero, our test statistic is getting higher and higher, right? So if our test statistic is getting larger and larger, the p-value is getting smaller and smaller. If our p-value is getting smaller, it's more likely it's going to be less than alpha and we reject. Okay. So we'll kind of run through some examples here. There we go. So as long as we have sample sizes that are large enough, and now we say large enough, this generally means anything over 30. I think I didn't put it on this slide, but really anything over 30, we should have a distribution of these sample slope coefficients that is normally distributed around what that true slope value would be from the population data. So we call this asymptotic normality. We're going to be dealing with data sets that are over 30, so this is always going to be true for us, right? So we could do different types of hypothesis testing. We do right-tailed, left-tailed tests, two-tailed tests. We're always, in this sake of this class, for linear regression or for multiple linear regression, which we'll eventually get to, or simple linear regression for now, always going to start out assuming that that slope coefficient is equal to zero, right? Or that these two variables are not related. Right? If we can reject that, we'll say that they are related. So here's our steps, same as they were before. Determine the null and alternative. I said that's always going to be this third one here. We're always going to start out assuming that this slope coefficient is equal to zero. Right? So that's always going to be done for us. We have to figure out our level of alpha that we want to do the test at. Well, that's okay. We have our three kind of benchmarks we already talked about, 0.1, 0.05, 0.01, which would correspond to 90, 95, and the 99% level, confidence level. We are then going to figure out our critical value. So we should be using a student t distribution. Like I said, we can use those standard normal values to approximate as long as we've got a sample size over 30. All right, sorry, as long as we have a sample size over 100, that standard normal is approximately the same as our student t. We're going to have sample sizes well over 100. So we can kind of keep using those standard normal values to approximate. We then turn our sample slope coefficient into a test statistic, and we then compare that test statistic to our critical value. Or we'll see from this data output, once we have a test statistic, we should also be able to come up with what the p-value is, and then we could also compare our p-value to alpha, okay? So I already wrote this out for us, but in general, how do we calculate that test statistic? We take that coefficient estimate we found for the slope, we subtract this assumed true value of zero, and then divide by our standard error, right? So our standard error, we write it out a little bit differently. It's going to look something like this. So we've got the sum of basically the deviations of the actual y from the predicted y values. So this is representing our what? Our error term, right? So we're summing up the sum of our squared errors, dividing by n-2. We have two parameters, which is why it's no longer n-1, like when we had a sample mean. So when we had a sample mean, we were calculating one statistic. Remember, anytime we're estimating our slope coefficient, we're also simultaneously, we said we're minimizing the sum of our squared errors. We took a derivative in respect to the slope and the intercept. So we're estimating two parameters, which is why we have an n-2 here. Okay. So let's just go back to an example we used last class, and my lecture slides are messed up. I guess ignore these, just large number down here. But if I were to run this regression where I'm trying to predict income, that's my y variable, with the number of days someone uses marijuana each month, I run this linear regression in Stata, and we had this coefficient we interpreted last class, which is for every additional day of marijuana usage each month, the predicted income or expected income goes down by $253. Now notice, not only do we get this coefficient estimate here, Stata will also give us our standard error associated with that coefficient estimate. So it will also then, well, pretty easily, it always assumes, unless we tell it otherwise, which we're not going to, that we're assuming there's no relationship. So it'll take that coefficient, subtract 0, and then divide by the standard deviation to give us our test statistic here. So negative 253 divided by 48 is what gives us that test statistic of negative 5.23. It then also uses that test statistic, looks at the sample size, actually uses the student t-distribution associated with that sample size, not even using standard normals to approximate here, and gives us what the p-value would be for this two-tailed test that we said we're always using. Right? So now it becomes pretty easy. I can do one of two things. I've got my test statistic, I've got my p-value. So what I could do is say, well, look, I could do one of two things. First of all, the easiest one would probably be to say, okay, look, the p-value that Stata gave me was 0. I always reject if the p-value is less than alpha. I can compare to my 3 benchmark alpha values. So is it less than 0.1? Yes. So I reject at the 90% level, confidence level. Is it less than 0.05? Yes. So I reject at the 95% confidence level. Is it less than 0.01? Yes. So I reject at the 99% level. So not a very interesting one here because the p-value is so low. Now, if I wanted to, I could also set this up and say, well, if I use those kind of standard normal approximate values, what would my critical values be? Well, starting out, we said at that alpha of 0.1 or the 90% confidence level, this would be negative positive 1.65. So my rejection region would be anything to the right or left of those values. My test statistic was negative 5.23. That is very clearly in my rejection region, right? I could then do the same thing, plot negative 1.96, positive 1.96, negative 2.58, positive 2. It doesn't matter here. I've got a large enough test statistic. It's going to be in my rejection region at every single level. So I can use the critical value approach. I can use my p-value approach. Both of them should lead me to the same rejection decisions. Okay. All right. Here. I think that's the one that I want. Hopefully this is recording in the order that I want it here. So here we've got reject. Right? If I'm looking at a different example, so we did this one last class as well. This is the number of bursts in the total shale wells. So we could come up with a coefficient estimate and interpret that. Right? Oops, sorry, hit my mouse on accident. But if I take that coefficient estimate, notice for this linear regression, that standard error was huge. So if I'm calculating my test statistic, I would take that coefficient, go back here, I would subtract the assumed true value of 0 and then divide by that standard deviation. Right? So if I take negative 3.9, divide it by 81, I'm getting a test. Oh, sorry, my mouse is being, I'm going to turn my mouse off and use this. There we go. So if I take negative 3.9 divided by 81, I'm getting a very small test statistic, which means that my p-value is going to be very large. So once again, I could use the critical value approach. That test statistic isn't going to be anywhere close to being in my rejection region for those kind of benchmark values of 1.65, 1.96, and 2.58. Now I could also use my p-value here. Is my p-value going to be less than my alphas of 0.1, 0.0? Not even close, right? So here I've got an example where I would fail to reject the null. So in this example, even though I came up with a slope coefficient estimate that told me that when the number of shale wells in the county went up, the number of births went down, I can't say with any reasonable level of confidence that there's any relationship between these two variables or that the number of shale wells is actually having an effect on the number of births. Now, for the number of days you use marijuana and income, I can say that there is a significant relationship between those two variables. Okay. All right. So we also talked about building confidence intervals, right? So I can build these confidence intervals for my slope coefficient estimate. Excuse me. And when we did this, and I used X instead of Y here, I should have kept this consistent with what I was writing on my DocCam here. But basically, if we have our sample mean, we build our confidence interval around that, going a certain number of standard deviations to the left and to the right. Right, that was our kind of t-value here. And then we multiplied it by the standard deviation of that sample statistic, which was our sample mean. So instead, when we have these slope coefficient estimates, I'm building my confidence interval not around my sample mean, but my coefficient estimate, which is right here. I'll go a certain number of standard deviations to the left and to the right. So here, what it always defaults to in terms of what Stata will give us is the 95% confidence interval. So if we look back at what I wrote down earlier, the standard normal value that would approximate that would always be going 1.96 standard deviations to the left and to the right to build that lower and upper bound. Now, Stata is actually going to use not the standard normal approximate value, but the value that would come from a student t distribution for whatever sample size we have, in this case, what, 170. So it is going to calculate our lower and upper bound even a little more precisely than if we were kind of doing this by hand and using a standard normal value to approximate here using 1.96. And then instead of multiplying by the standard deviation of our sample mean, I said we'll multiply by our standard error, which we can kind of think about as the standard deviation of our slope coefficient estimate. It's not theoretically the correct way to say that, but it's an easy way to think about that comparing it to things we've already done. So notice here, my 95% confidence interval, does it include the assumed value of 0? Yes, right? Negative 164 to 156, that includes 0. I basically, any value in that 95% confidence interval, I can't reject as what could be the true slope coefficient estimate. So even though we're always doing our hypothesis testing for the assumed true value of 0, what this is telling me is that for a two-tailed test, if I were to assume that that slope coefficient was anything in between these values, I would always fail to reject that null. I can't say what the value is. It's with 95% confidence, it's one of the values in between 164, negative 164 and 156. Excuse me. But I don't know which one. Now I can say it's not negative 180 or it's not 230, right? Based off of my sample data. But any value in this range, I would fail to reject the null if I ran a hypothesis test for it. So if we go back to our other example, notice here, well, now I've got a 95% confidence interval. It only includes negative values. So what this is saying with 95% confidence, the relationship between marijuana usage and income is somewhere in between negative 350 to negative 158. Well, one of the values that's not in that range is 0. So this is telling me with 95% confidence, the true slope coefficient is somewhere in this range. If it doesn't include 0, then I can reject 0 as a possibly true value, right? So those are kind of two examples, thinking about how we compare, use confidence intervals as well as do hypothesis testing. So here, my interval includes 0, so I fail to reject. Okay. This one didn't include 0, so I could reject that assumed true value of 0 or that there was no relationship. So ultimately, if we make a rejection decision or our confidence interval does not, if I make the rejection decision to reject or my confidence interval doesn't include 0, I'm saying that I found significant evidence there's a relationship between this x and y variable. If I fail to reject the null, that the relationship is equal to 0, or 0 is included in my confidence interval, I didn't find strong enough evidence to say that there is a relationship. So I have to default to the assumption, which is that there's no relationship. Okay. This is just a little bit of, I won't go, we'll probably talk more about this as we go through more examples, but everything that we've talked about up to this point in this video is about statistical significance. So can I reject the null that the X variable has no effect on Y? At what levels can I reject it? Does my confidence interval include 0? However, even if we don't have statistical significance, or even if we do, we might or might not have economic significance. So economic significance, we think about, are these estimates large, right? So sometimes these two things don't go hand in hand, right? So even if I find something that is statistically significant, so when we have large enough data sets, I want to kind of prove this here, or at least kind of walk you through this thought process. So if my test statistic is calculated by taking that slope coefficient estimate, now remember, we're subtracting this assumed true value, but it's always 0, and then dividing by my standard error. Really, all we're doing is taking that slope coefficient estimate divided by the standard error. Now remember, this standard error, we had the sum of my differences between the actual y, predicted y, or kind of my errors I'm making here, over n minus 2. So if I take large enough sample sizes, what's going to happen to this fraction? So my denominator is larger, this is going to go down. If my standard error goes down, what's happening to my test statistic? It's going to go up. If my test statistic goes up, what's happening to my p-value? It's getting lower, which makes it more likely I can reject the null or that I find statistical significance. So finding, the day we live in now, we can have huge data sets, tons of observations. It's sometimes easier to find statistical significance. Okay? So just because we have statistical significance, if, for example, I were to look at that estimate, and let's say it was 0.00000001. Okay, if X goes up by 1 unit, Y changes, but it barely changes, right? There's not a lot of economic significance there. So even if we have statistical significance, especially with large data sets, we also want to make sure we have economic significance, right? Now, the reverse can happen as well, right? What if I have something that's statistically not significant? Well, if I have a really small data set, everything works in reverse, it actually makes it less likely I can reject the null. So with small data sets, even if we don't have statistical significance, if the estimate is really large in magnitude, we might have some economic significance. We shouldn't just throw those results out completely just because we don't have statistical significance. So in an ideal world, we'll have both, right? But if you're going out and looking at research that's been done, a lot of the times, really in any science, we sometimes throw out results just because we didn't find statistical significance, but especially with small data sets, um, no statistical significance, but having some economic significance might still be important, right? It might still tell us that, yeah, we don't have a lot of, statistical evidence, strong statistical evidence that there's a relationship here, but it looks like, based on the magnitude, that there might be something going on. Also, as more of a, before we kind of progress to the next topic, just to kind of make a point as we start going through these, I might find, let's say I found a p-value and it was 0.81. No, sorry, not 0.81. Let's say I found a p-value and it was 0.19. Well, that's not going to be less than any of our conventional alphas, right? So we're going to fail to reject at every single level. However, remember, this corresponded to what? 90, 95, and 99% confidence. What levels could I reject at? Well, let's say I wanted to say something with 80% confidence. What would my alpha value be? 0.2. Is my p-value less than 0.2? Yes. So I could reject, or I could find statistical significance at the 80% level. Now, it's not as high as we typically like, so it doesn't meet kind of our scientific standards, but that's not nothing, right? It shouldn't just be completely ignored. So we'll be a little bit careful when we're looking at these results, just not to like throw anything out just because we don't reject at our kind of highest conventional levels. All right, I'm gonna end this video here, and we'll kind of pick up on the next topic in the next video. So I'm going to combine two videos I recorded at separate times, but just to revisit, when we were thinking about the distribution, this is the idea that we only see a slope coefficient from one sample. But if we were able to take, say, 1,000 samples from a population data set, obtain 1,000 different estimates for our slope coefficient, as long as we had a sample size over 30, that was that central limit theorem, then those slope coefficients should be normally distributed around whatever, well, I put 0 here, whatever that true coefficient would be if we estimated it from population data, okay? So I'm going to try to prove this to you. We kind of had that standard error, which was the square root, the sum of y minus the predicted y squared over n. So we said as we have larger sample sizes, it should decrease our standard error, right? That was just some of the things that we had talked about. So I'm going to try to prove this to you with some data and stata, pushing you guys, not pushing you, pushing it a little bit further than I would expect you guys to do. But I think it's helpful to kind of see the power of stata, but also kind of proving some of these concepts with data. So I've got this, where's that? COVID County data pulled open. So we're going to go down here. So just to kind of, if you were doing this from scratch, we'll kind of open that COVID County data up. I'm going to scroll down here. And here's this extra proof, right? So let's say I'm interested in the relationship between the percent of a county vaccinated and the cases per person. This is an example we used on Tuesday. So I've got not dummy variables, I've got nice continuous variables here. I'm going to run a regression. I have every county in this data set. So I can kind of think about this as like essentially population data, right? So this is really the true coefficient or the true slope coefficient between the percent of the county vaccinated and the cases per 1,000 people. And then I can think about like my true standard error, right? This isn't completely usable because Stata still treats this like a sample. It doesn't identify as population data. But for the sake of what we're doing, this is the kind of true coefficient. So I'm going to create this program. I'm going to clear out programs and create this new one, which I'm going to call coefficient estimate. I'm going to use that COVID County data. I'm going to sample 30 observations from that data set. So if we look at the actual data, there's 3,000 counties. I'm going to sample 30 random counties. I'm then going to run that same regression and obtain the slope coefficient on my X variable. So that's all this code does. Once again, I'm not going to expect you to do this or use this on any problem sets, but I'm kind of trying to show you the power of what you can do. You can kind of start to create your own programs. Also, when you run a regression, and we'll start using this down the road, but those regressions have stored behind the scenes different values you can get. So notice like when I run this regression, I see negative 0.25. I can grab that value. I don't have to like type it in. It's stored behind the scenes as _b and then whatever that X variable is called. So that's all that's doing. It's grabbing that value from that Stata output. So I'm going to define this program and then going to run this 100 different times. Okay. Now, I was only going to do 100 in class. We'll see. I think with my computer, since I'm not relying on Wi-Fi, I'm going to try to run this 1,000 times. So what this is going to do is it's going to randomly sample 30 observations, run the regression, save the coefficient estimate for the slope. Run this again, different random 30, save the coefficient estimate from this regression. It's going to do that 1,000 times. It's then going to, so I'm going to save all those 1,000 different sample coefficients. Let's see how quickly this runs. I might have made a mistake doing 1,000 instead of 100, but there we go. So what I now have is 1,000 different estimates for what that slope coefficient is. Notice they're all different because they're all different random samples. However, if what I told you is true, when I summarize these slope coefficients, these 1,000 different estimates, they should be centered around that true estimate. Okay, so I'm going to summarize these. Okay, and sure enough, they're centered around negative 0.252, which pretty close to the true pot, right? In theory, what I would need is not 1,000 different coefficients here. I would need an infinite number. I can't really do that. And you know, I could do up 10,000, but it would just take forever, right? But it's going to get closer and closer the more samples I take to finding that true population mean estimate for what that slope should be, which is negative 2.546. Now, this isn't exactly correct, but I can think about the standard deviation of those 1,000 different slope coefficients. I said we can kind of think of as our standard error as the standard deviation of our slope coefficient. It's not completely correct to say that, but it's for the sake of what we're doing and conceptually, it's okay to think about it that way. So that standard deviation of these 1,000 different slope coefficient estimates kind of represents my like standard error. Okay. So if I do the exact same thing, I'll change this to 1,000. But instead of sampling 30, I'm going to sample 100. So what did I say when I was kind of first starting this out? Well, when we have higher sample sizes, what should happen to our standard errors? Well, it was in the denominator of our standard error calculation, so it should decrease it. So if I were to do this exact same thing, I'm going to now sample instead of random 30 observations, random 100, run the regression, save that coefficient estimate. I'm going to do that 1,000 times. I'm then going to summarize those coefficient estimates. I should see that they're still centered around that true population coefficient of negative 0.25 about, but I should also see that when I do a higher sample size, that standard error or the standard deviation on those estimates should be lower. So I'm going to run this. Should take a little bit longer since they're larger samples and I'm doing 1,000. If you're trying to reproduce this, I would do 100 just to make sure you don't freeze your computer. Sure enough, they're still centered around, and notice with larger sample sizes, I've still got this unbiased estimate, all right? It's still centered around that true coefficient when I was using the population data. Now, what's also true is when I take higher sample sizes, what happened to that standard deviation of my coefficient estimates? It went from 0.23 to about 0.12. So it is decreasing. So I'm getting more consistent estimates, right? That variation I'm seeing in my estimates is going down, which that's good, right? I mean, we don't want to have a lot of variation because in practice, we don't have 1,000 different samples. We only have the one sample that we have, right? The only data set we have, okay? Okay. So is there anything else I want to say here? Oh, this isn't going to be perfect because it doesn't give me a nice smooth line. Oops. But not only should they be centered around that true mean coefficient, they should be normally distributed, we said, if we had sample sizes over 30. So if I use the histogram command, it gives me a histogram, which isn't like a nice continuous line, but you can kind of see from here, oh, it's pretty close to a normal distribution, right? And in fact, if I go back and use 30, do the same thing. It's still pretty close to a normal distribution, right? But I want to use 1,000 here. Whoops. So we'll go back to the sample sizes of 100. But notice both of them nice and normally distributed. Okay. All right. So the next thing I'm going to do is also kind of give you proof of these confidence intervals. So we said we can use hypothesis testing to make our rejection decision. We can also see, does our confidence interval include that assumed true value of 0? So what I can also do is show that not only something about the distribution of my sample slope coefficients, but we said, just like with the sample mean, so if my sample slope coefficients are normally distributed around whatever that true value should be, then anytime I take one sample, and I'll use red here, whatever sample coefficient estimate I see, if I build a confidence interval around that to get my upper and lower bound, if in building this confidence interval, remember, how do I do that? I go a certain number of standard deviations. What's the standard deviation of my coefficient estimates, my standard error? If I go a certain number of standard deviations to the left and the right, whatever confidence level I'm choosing, so here I'm going to say, let's build a 90% confidence interval. So that would correspond to an alpha of 0.1. So if I look at my standard normal value that approximates that, it's about 1.65. I think in the Stata file, I go out to the third decimal. So if I go 1.645 standard deviations, or that standard error to the left and the right of that slope coefficient estimate, 90% of the time, I'm going to have a confidence interval that includes whatever the true value would be if I had the population data. Now, 10% of the time, I'm going to end up with estimates when I build this confidence interval that don't include that true slope coefficient estimate. So we can do this in Stata as well and kind of prove this to ourselves. So I've got what were we working with before, just in case you're kind of restarting this video. Well, actually, we're down here. Let's use the samples of size 100. And this is where, we took 1,000 different samples and we kind of saw, okay, not only are they centered around whatever that true slope coefficient estimate is, which was what, negative 0.2546 when we just ran this from the population data. We also saw that they are normally distributed, right, when we did that kind of histogram command. But what's going to be the case is, and here my data is now these 1,000 different sample coefficient estimates, okay? So they're all a little bit different than that true estimate of negative 0.259 or negative 0.25, that wasn't quite 9, it was what? Negative 0.2546. So what I'm going to do is I'm going to say, okay, I'm going to build a 90% confidence interval for every single one of these sample coefficients. How am I going to do that? I'm going to go 1.645 standard deviations to the left and the right. What is my standard deviation? It's my standard error. So I said we can think about this standard error that I had from these 1,000 different sample coefficients was essentially like the variation that existed in these 1,000 different sample coefficients. So I'm going to use 0.1, not 24, 1.1228. So let's just be a little more precise here. Is that what it rounds to? Nope. I round to the fourth decimal, 0.1129. Okay. So I'm going to create my lower bound by going 1.645 standard deviations. Well, what's the standard deviation of my sample coefficient? That's my standard deviation I'm grabbing right here, kind of representing my standard error. I'm then going to do the same thing to create my upper bound, but I'm going to add that many standard deviations. So run this. I've now got my data where I've got, oops, what didn't it like? Oh, I forgot to rename it. So I'm just going to rename these coefficients as my sample coefficient and then create the upper and lower bound. So now for every sample that I took, I've got a confidence interval, right? The upper and lower bound. I'm then going to create a new variable, which says, okay, if this true slope coefficient of negative 0.2546, which is what I got when I ran this regression for the population data set, if my confidence interval includes that, so if my lower bound is below that and my upper bound is above that, then I'm going to put a 1 in here for this variable. So you'll notice if I create this, every time I've got an upper and lower bound where negative 0.25 is in that range, I get a 1. If I ever have one where here, negative 0.254 is just outside of my confidence interval, this variable is a 0. So what should be the case if what I was saying is true is that when I summarize this new 1, 0 variable that I created, 90% of the time, my confidence interval should include that true population value, which means 10% of the time it wouldn't. So when I summarize this 1, 0 variable, I should get about, well, what would 90% be if I have a 1, 0 variable in proportion form? About 0.9. So if I summarize this, well, yeah, sure enough, I'm getting something close to 0.9, right? Now it's going to be a little bit off because it's always a different 1,000 random samples. So I could run this again. And instead of 0.91, I'm going to get something that's, whoops. So 0.913, I could kind of, well, actually, sorry, I shouldn't have been using point. So this is 0.1186. So I should have changed this. So, well, here, I'll show it to you again. So let's say I take another random 1,000 samples of 100. Now I get that standard deviation is 0.1232. So 1232. So now when I do this, I'm not getting 0.91, I'm getting 0.902. So it's going to be really close. Obviously, like I'm only doing this with 1,000. To really get exactly 0.9, I need an infinite number. But this, I think, kind of goes to show you with some data, like what we said is, is true about these confidence intervals is true. And about 90% of the time, we're going to have a confidence interval that includes that true slope estimate, right? Even if we're only doing it from random 100 samples out of that like 3,200 person or county population data set. Okay.